Okay, chemists, in this lesson we're going to look at clusters of atoms that exhibit the same types of chemical behavior. We call those things functional groups. They're sort of like polyatomics in that they're clusters of atoms, but they're found in organic things, and they're not ions. They're just clusters of atoms bonded in a unique way. To illustrate this, I have an example of a molecule called Taxol. This is a very famous molecule. It's naturally occurring, and hopefully you can appreciate just the complexity of having to assemble something like this artificially. Well, it's been done many times. This has been a molecule that chemists have been able to build in the lab, and it is chemically, structurally, and biologically identical to what we see from nature. It's just not sourced from nature. And that's a big goal of organic chemistry, is how to make molecules synthetically as opposed to sourcing them naturally, and then how to make things that are not naturally occurring, maybe they are even better than the naturally occurring one. Anyway, let's take a look at some functional groups that we see. Most of the ones that you have to know you might recognize from your 10th grade class. I'll highlight them, circle them here, and then we'll draw an example of one. That one right there, I'll start with as number 1. This combination of a carbon-oxygen double bond attached to a nitrogen on one side and a carbon on the other, that's called an amide. And I'll sketch what an amide looks like right next to it. That's when you have a carbon-oxygen double bond with a carbon on one side and a nitrogen on the other. Usually the nitrogen is bonded to other things, obviously. Secondly, up here we have another carbon-oxygen double bond with a carbon on one side and an oxygen on the other. That's called an ester. Carbon-oxygen double bond, carbon on one side, oxygen on the other. Specifically, the ester has an oxygen that's attached to yet another carbon. We'll see there's some other functional groups where this is not a carbon, but maybe a hydrogen that actually has a different name. The third one, what if we have a carbon-oxygen double bond that's just flanked by carbons on both sides, like that one? That's called a ketone, Ketone. So this is a carbon-oxygen double bond with a carbon on both sides, and then those carbons are attached to other things. Moving on, we get to more simple ones. There is an OH group attached to a carbon. That's called an alcohol. So just a C attached to an OH and nothing else interesting. If there's other stuff maybe on that, it's no longer an alcohol. We'll see that in a moment. But if it's just singly bonded to other things, you would call it an alcohol. Here in this little four-membered ring is a carbon-oxygen-carbon bond. That's called an ether. Sort of looks like organic chemistry's version of water, where instead of H's on both sides, you have carbons on both sides. So no doubt that's a bent polar geometry in the middle of that. Moving on, let's go to like the middle of this. What about this functional group here? This is a carbon-carbon double bond. That's called an alkene. And then I'm going to list number 7, just hydrocarbons. Arguably, this is not a functional group, but if you have nothing but single bonds with hydrogen and carbon, that's just called an alkane. And some folks would say that's not even really a functional group because it doesn't do much chemistry at all. You can pretty much just burn alkanes for fuel purposes, or you can substitute them. You learn in the Orgo class. So those 7 are all present in this Taxol molecule, and sometimes there's multiples of them. The ester I pointed out here, there's also another ester down there, there's another ester over there, there's another ester right there, there's an alcohol right there, so there are several examples, at least in this molecule. There's 4 others that I want you to know that are actually not in the Taxol molecule, starting with what's called an amine. Right below the amide is where I put it. And this is not as complicated as an amide. It's just a nitrogen with 3 single bonds to hydrocarbon or simple things. In other words, not right next to a carbonyl. You have to have this combination to be called an amide. Without that carbonyl, then it would just be called an amine, if you know what I mean. Below that, how about a carbon-oxygen double bond with a carbon on one side and an OH on the other? This is really similar to an ester, but instead we have an OH attached. That's called a carboxylic acid. Carboxylic acid. And similar to the acid, but let's take the oxygen out of the game and make it a carbon-oxygen double bond with a carbon on one side and an H on the other. That's called an aldehyde. Again, these are things that just happen to not be in the Taxol molecule, but I still think they're useful functional groups for you to know. And then finally, number 11, you saw the carbon-carbon single is an alkane, the carbon-carbon double is an alkene. What about a carbon-carbon triple bond? That's an alkyne. Okay, now there are certainly other functional groups out there, dozens more that you would learn in a typical undergraduate organic chemistry class, but here we're just introducing some basic high school level organic chem, and those are the 11 that most high school students learn. So let's practice this. You're all perfectly well adversed at using line structures, and here are two well-known molecules. This is erythromycin, and then indinavir, a drug molecule on the right. I want you to just see if you can find some examples of functional groups and maybe circle them and write the name of that functional group next to it in the structure. So hit pause and try that right now. See if you can get at least 2 in each of the molecules, and then we'll go over it. Okay, let's see how you did. So let's start with the erythromycin molecule. I'll just circle the ones I see. Here's a nitrogen with all single bonds around it. That's an amine. Down here in the lower right, that's an alcohol, the OH group. I see other alcohols. There's another alcohol up there. If you listed it more than once, that's okay. At the very top of the molecule, there's a ketone. Carbon-oxygen double bond flanked by only carbons. I'm not going to list them, but there's another alcohol. There's another alcohol. What about this carbon-oxygen double bond? Well, that is an ester, as denoted by the fact that you have a carbon-oxygen double bond, an oxygen carbon on one side and a carbon on the other. Pretty specific arrangement of atoms in order to be called an ester, and that's what many of these functional groups are. They have a very specific requirement. If you wrote ether for one of these groups down here, you would not be wrong. I'll just tell you that actually it's a little bit more complicated than an ether. This is called a acetal, which is not one from your list up above, but it lets you know, oh, if you have what looks like a double ether, it's actually no longer just an ether, and you can see that there's one carbon here that's sort of being shared by 2 what look like ether groups, and that's exactly how you could describe it. But the chemistry is a little bit different than what we see with just a regular ether, so we give it its own name. So if you want to know, I'll highlight, there's actually another one up here. Highlight that a little bit less broadly. There's actually another one right there. It's called an acetal. You do not need to know this. We don't learn this until the second semester of the Orgo elective anyway. All right. Let's take a look at the indinavir molecule. There's a couple of others. We have an alcohol on the left. There's an amide right below it. That's a carbon-oxygen double bond with a nitrogen on one side and a carbon on the other. In fact, there is another amide right there. So I have an amide and another amide. I have another alcohol down there. We have an amine over here. We have a couple of amines. If you circled one of these carbon-carbon double bonds and wrote alkene, fair game. However, when you have this what looks like alternating arrangement of single and double bonds, especially in a 6-membered ring, it behaves a little bit differently than a regular alkene. So I'll teach you what this really is. This is called an aromatic ring, sometimes called an aryl ring. And this happens to be a benzene ring. Many of you have probably seen that already. We certainly have when we talked about resonance. There's another very similar group over here that's almost like a benzene ring, but it's got a nitrogen in it. It's called a pyridine ring. Now, these are not things you need to know for this level of the class. I'm just showing them to you to give you a sense that there's a lot of other groups out there. There's a name for everything, essentially. And organic chemistry is not about naming things. It's about how we use these chemical compounds to make molecules and learn how they behave with each other. This introductory stuff is very introductory. But let's do a little naming anyway and learn how we name things that contain functional groups. The functional group will tell you how you change the suffix of the name of a chemical compound, and they are prioritized from things with very high priority like carboxylic acids to things that are fairly low on the list like alkynes, and all the way to really low on the priority list things like ethers. If you have multiple functional groups, you go with the highest priority group, but let's look at a few and see if we can figure out what the structure would be from the name. The first one, 2,5-dimethyl-3-hexanol. The first thing I look at is the end of the name, the OL. That means we have an alcohol, because that chart on the right tells me it's an OH group. Then I go to hex. That's 6 carbons. And now, what's the 3? Aha, that's where the all is. So along a 6-carbon chain, the alcohol will be on the 3rd carbon in. So now I'm ready to start drawing. So I'll draw a 6-carbon chain using line structures. 2, let me use an actual pen. 2, 4, 6. If I number them in my head, 1, 2, 3, 4, 5, and 6, I would have an alcohol on the 3rd carbon in. I would have a methyl, it looks like, on carbons 2 and 5. So I'm going to move this just a tad and then draw my OH on the 3rd carbon from the left. If you did it from the right, you'll still get the same thing. It'll just be upside down. Then I have 2 methyls because of the dimethyl, and they're on positions 2 and 5. So position 2 gets a methyl and position 5 gets a methyl. That's 2,5-dimethyl 3-hexanol. Notice every single part of the name is meaningful in terms of what that structure looks like. All right, B. B is 5-bromohexanal. The al at the end means an aldehyde, and hex means it's a 6-carbon chain. So I again have 2, 4, and 6. Now they didn't tell me where the aldehyde is, but go back and look at what an aldehyde looks like. The aldehyde can't possibly be in the middle of the carbon chain. It has to be at the end. So we don't even bother giving it a number. That's what an aldehyde looks like. And actually, if you're doing a line structure, you don't need to draw in that H, do you? It's implied that it's connected to that carbon. Why isn't it in the middle of the chain? Why don't I have a carbon-oxygen double bond there? Well, that's not an aldehyde. That's a ketone. So I know it's got to be at the end of the chain. So it's position 1. What else is in this molecule? It says that on carbon 5, there is a bromo. That must be a bromine. So simply attach a bromine to carbon 5. That's 5-bromohexanal. Lastly, 7-bromo-3-nonanone. The one means we're a ketone. That can be in the middle of the chain, and it's on carbon 3 of a 9-membered chain. So 2, 4, 6, 8, and 9. I go in 3 carbons, and I have a ketone, and then I have a bromine on carbon 7. 1, 2, 3, 4, 5, 6, and 7. So that's where I put my bromine. You can see halogens are just named as if they're branches. They're so low on the priority list for functional groups. I didn't even mention them, but you call them halides attached to carbon groups. All right, hit pause one more time and try this challenge question. Draw and name 3 different isomers of C3H8O. At least start with drawing them, and then we'll see if we could actually name them. Okay, so C3H8O. I'm going to start with just 3 carbons in a row, and then I'm going to put an oxygen at the end of the chain, and then I'll check, how many atoms have I used in terms of the H's. Well, I've got 3 H's there, 2 there, 2 there. I need 1 more. Good, I'll cap off that oxygen and make it an alcohol. So this is an alcohol, so it's going to end with all, and it's 3 carbons. 1, 2, 3. Actually, 1, 2, 3, right to left. Alcohol gets position 1. So this is 1 propanol. That tells me where the alcohol is and how many carbons it is. But that's only one isomer of C3H8O. You could also draw a 3-carbon chain with an OH in the middle. This would simply be 2 propanol. And if you got the 3rd isomer, good for you. It's not an alcohol, though. It's an ether. It would have a 2-carbon group attached to an oxygen and a 1-carbon group on the other side of the oxygen. Now, ethers, if I look at my chart over here, ethers are actually named as a branch, and it's okay if you didn't know how to name this, but what you do is you find the longest carbon chain, in this case 2, so this is an ethane derivative, and the ether gets named as a branch. As opposed to this being a hydroxy, this is a methoxy because it's a methyl and an oxygen. So this would correctly be called methoxyethane, where the methoxy is simply the branch, as opposed to a methyl. It's a methyl and an oxygen. Many simple ethers are named with their common name, however, so it's not out of the question if you called this ethyl, methyl ether, and that just describes the 2 groups attached to the oxygen on the ether. What's on one side, what's on the other, simply list them alphabetically, and in this case in higher carbon number as well. Okay, that's just a couple of examples to show you how to name molecules that contain functional groups, but more importantly, how to identify them. And again, we use these so that we can speak the language of organic chemistry and talk about the reactions that these things do.